Continuing with section 3.2, I next want to talk about the zeros of a polynomial function. The values of x for which f of x is equal to 0 are called the zeros. These values of x are the roots or solutions of the polynomial equation. Each real root is an x-intercept of the graph. Let's take a look at an example. Find all the zeros of the function f of x equal to x cubed plus 2x squared minus x minus 2. Again, another word for zeros of a polynomial are the x-intercepts. And in order to find the x-intercepts, we plug 0 into y. So setting our function equal to 0, we'll get 0 equals x cubed plus 2x squared minus x minus 2. In order to solve this polynomial, I see 4 terms, so I'm going to use the cut in half factoring technique to solve for x. GCF out of the left is going to be x squared, leftovers, x plus 2. GCF on the right is negative 1, leftovers, x plus 2. Pulling out x plus 2 in common, I'm left with x squared minus 1. Continue factoring, I see difference of squares, so I have x minus 1 times x plus 1. In order to solve for x, I'm going to set each expression equal to 0 and solve for x. Subtracting 2 to both sides, I get x equals negative 2. Adding 1 to the other side, I get x equals positive 1. And subtracting 1 to the other side, I get x equals negative 1. So again, for this polynomial of a degree 3 polynomial, I have 3 solutions, 3 zeros, or 3 x-intercepts. Next, I want to talk about the multiplicity of x-intercepts. The multiplicity represents the exponent on each zero. If it's an even exponent, that means when I graph the polynomial, it's going to touch the x-intercept. But if the degree is odd, or the exponent is odd, then it's going to cross when I graph the x-intercept. Let's take a look at an example. Find the zeros, multiplicity, and state if it crosses or touches the x-intercept for the following polynomial. F of x is equal to x minus 2 cubed times x plus 5 squared times x minus 4 to the 5th. So first, let's find the zeros. To find the zeros, set each expression equal to 0 and solve for x. Adding 2 to both sides, I get x equals 2. Subtracting 5 to the other side, I get x equals negative 5. And adding 4 to the other side, I get x equals positive 4. So 3 zeros in this problem. Next, I want to describe the multiplicity. The multiplicity, again, is the exponent on each zero. So for the first one, the multiplicity is exponent 3. For the second zero, my exponent is 2. And for the third zero, my multiplicity is 5. Next, let's determine if it's a cross or a touch. If my multiplicity is an odd number, which 3 is an odd number, that means when I draw my graph, it's going to cross the x-intercept. Next, my multiplicity is an even number. That means when I draw my graph, it's going to touch the x-intercept. And again, multiplicity of 5 is an odd number, so that will cross when I draw my graph. Next, I want to talk about the intermediate value theorem. This states if f of a and f of b have opposite signs, then there is at least one value of c between a and b for which f of c equals 0. This is better shown with an example. So, let's show that f of x equals x cubed minus 2x minus 5 has a 0 between the numbers 2 and 3. So all I have to do is plug in 2 and plug in 3 into my function and look at my result. If one result is positive and one result is negative, that means it must have crossed when I drew my graph somewhere between 2 and 3, which means there must be at least one 0 between 2 and 3. So let's plug in 2 first and see what we get. So that's 2 cubed minus 2 times 2 minus 5. Simplifying, I get 8 minus 4 minus 5, which is -1. Let's plug in 3 next. 3 cubed minus 2 times 3 minus 5. I get 27 minus 6 minus 5, which is 16. So since this result was negative and this result was positive, we have just showed that there must be some 0 between 2 and 3 because we had a sign change. We will mostly focus on graphing polynomials in the next course, Pre-Calculus, Math 11-13, but in the next video I'll do an example of graphing so I can put all the pieces together that we've done in this section into one graph.